I cannot. Is it working? Okay. Yeah, okay. Okay.
Our speaker is coming from Nomaten in Poland, and the topic is neural network interatomic potentials. Please go ahead.
Okay. Thanks for this opportunity. And my name is Amir. I have just finished my first year of PhD in Nomaten. And I've been working on developing a neural network interatomic potential for nanoindentation simulations. And in this work, I'm getting a lot of help from Franco Pellegrini, from CISA, Emine Küçükbenli from Harvard University, Javier Dominguez, our coworker in Nomaten, Professor Miko Alava, Professor Kaxiras, and my supervisor, Dr. Stefanos Papanikolaou. So I'm going to first talk about why do we need to develop interatomic potentials. And the thing that I can say is that not every kind of potential is good for a specific problem. For example, if we look at these two EAM potentials that were developed for nickel cobalt chromium, first one was developed by Li Shengma, and the other one was developed by Farkas and Caro. So in the upper one, you can see when we do Monte Carlo relaxations, you will see some nickel segregations. And the other one doesn't show anything. When you do relaxation, you cannot see any segregations of nickel, cobalt, and chromium, nickel or cobalt chromium segregations. And both of them are for the same material, but they have different properties, even mechanical properties in dislocation dynamics and stuff like that. So now I want to somehow talk about what is nanoindentation simulations. In nanoindentation simulation, there is a substrate that hits your surface, and you can get some information while heating your sample. Like pileups and plastic zoning, can see these things in your simulations and also compare it with experiments. Also, low depth curves, they can tell you information about hardness, about strength of your material, and stuff like this. This work was done by Javier Dominguez, and yeah. So in this work, what I'm going to talk about is how to develop your potential and taking care of your training data set. I'm using Beller-Parinello potentials. And as all of you know, it gives you these Beller-Parinello descriptors. And these descriptors are some vectors that you can use in order to fit your potential. So the way I am doing it is to indent a sample with an EAM potential, and then calculate all these G vectors, descriptor vectors, for all the atoms in the indented sample. And I got a training data set from literature, and I calculated all the G vectors also for the training data set. And then by getting the minimum distance, minimum Euclidean distance of all the atoms in the training, in the indented sample and the training data set, you can understand if you have enough information in your training data set to simulate your simulation. So how can we understand what is a good distance? The thing that I did was to create a distance matrix for the data set itself, and then the distribution, I mean, when the tail starts to become very narrow, I decided to think of that as a good distance. Like here, it would be 6. On the right, you can see the distance, the minimum distance of every kind of configuration that you have in your data set with each other. For example, everything is far from isolated atom or dimers, and the distance of the diamonds or A15 or what else I have, liquid configurations, they are far from indented samples. So I decided to remove them from the data set. Here I'm showing what I have removed and what I have kept from the dataset that I got from literature. And the first two, isolated atom and dimer, I removed them because there was a little number of them. Also, the self-interstitials, they were computationally expensive, and as you can see, there is a long tail. I think that comes from the interstitial region, but the bulk part gives you a good distance. But we have this information in the BCC distorted configurations. Also, I removed A15, C15, HCP, FCC, diamond, and phonon not phonons, just diamonds. And this is because I removed one by one these configurations, and I saw that the distribution of distances didn't change at all. And for the short range configurations, I also saw that because the distribution of the energies is very wide, you cannot get a good, let's say, validation error on the forces. So everything was good in this data set, and it could be improved for the dislocation cores. So when you indent the sample, there is some dislocations that happen in your in your configuration, and the dislocation cores has a long distance with your training data set. And we decided to add enough high temperature configurations to the data set. And after doing that, we saw that the distribution of the distance is reduced for these configurations. The same thing that we did for the regions under the indenter was to increase the temperature of the atoms in a bulk BCC crystal, and then just keep one layer of them freezed, because it can somehow capture the, let's say, interaction of the indenter with your sample. And this also helped in order to reduce the distances of the training data set with the indented sample. The second thing was the pileups, which is the atoms on the surface, and it gives you information in experiment. And you can see that by adding some surface configurations, again keeping a layer freezed and the other atoms at high temperature, you can decrease the distances of the training data set to the indented sample. So another way of treating the dislocation cores was to use generalized stacking fault configurations. And in A, you can see one configuration of that. On B, you can see the distances of a BCC distorted with the dislocation cores. On C, you can see the gamma configurations distances with the indented sample. You can see that on the slip plane, the distances are good, but on the dislocation core on top, everything is a mess. So if you add an interstitial on a gamma surface, and again calculate the distances of the your configurations, gamma with the self-interstitial, to the dislocation cores, you can see that it is improved. And why it is better than the high temperature configurations? It could be because high temperature configurations have a very large distribution of the energies, and while training them, it could be very hard, and you cannot maybe get a good validation. So then after training, you can see that we got some good results for energy root mean square error, for the configurations that we added to the data set. We also added some compressed configurations, but the force RMSE is the best that we got these numbers. And this is the elastic constants that we got from the train potential, and also the distribution of the energies and forces after on the test set. And this is not finished. This is ongoing on progress work, and we are trying to make the potential faster and then validate everything with the indentation simulation with the neural network interatomic potential. Thank you.
Okay, thank you very much for a very interesting talk. Any questions about this work? Yeah, Claudia.
Hi, thanks
Hi.
for the nice talk. Just a question on the last thing you said. How would you make the potential faster?
We want to decrease the descriptor length, decrease it as much as possible, and to see if the validation is going to, I mean, the validation is not going to change. This is the best thing I can do. So I don't have any other ideas. Yeah.
Any further questions or from Zoom? Maybe I have one. So you've shown quite a thorough comparison to many other interatomic potentials, and I think these days it is known that these potentials are working fairly well in your field. So what is the next step for you, and where do you think is the challenge with these potentials? Is there something that is still not working well, and do you think people need to work on it?
Yeah, for example, there's a work for tungsten, also a BCC metal, that the surface, these pile-up patterns, the pile-up patterns that I showed on the second slide, I think. Yeah, figure A. This is something that can be experimentally compared with simulations, and not all potentials can give you the exact pattern as experiment. This is something that could be really compared. Also, the energy, I mean, the energy of surface configurations, we can compare with DFT and see if they are close.
So what do you think would be the solution there? To sample more in particular
Well,
configuration areas, or?
the solution that we came up for the surface configuration was this: to add these configurations, one layer of them freeze and the other atoms to be at high temperature, to somehow get the catch the energy from these configurations for the surface.
And do you see these kinds of choices? I mean, now you've come up with this choice, you've implemented it. Do you see these kinds of choices being automated in the future?
Like by active learning?
Something like that.
I haven't thought about that, but maybe.
I hope you get inspired at this workshop.
Yeah, sure, yeah.
Okay, if there are no further questions, then another round of applause for our speaker.
Thank you.